In the early autumn of 1849, as the nights lengthened and the air carried the first hint of cold, a woman named Harriet Tubman moved silently through the forests of Maryland. She traveled without maps, without certainty, guided only by memory, instinct, and an unbreakable will to be free. By day she hid, by night she walked. When supplies ran out, there were no markets, no handouts, no safety nets. Survival depended on the land itself, and the land answered. Along riverbanks and forest edges, trees heavy with pale green fruit waited in silence. For a few brief weeks each September, they offered calories, nourishment, and something just as vital, hope. This fruit was not exotic, yet it tasted like the tropics. It was not cultivated in rows, yet it fed generations. It was pawpaw, Asimina triloba, the largest edible fruit native to North America, and for centuries it was woven into the survival story of this continent. Pawpaw is a contradiction by modern standards. Its flavor suggests islands and sunshine, banana, mango, pineapple folded into a soft, custard-like flesh, yet it grows naturally from the humid forests of the eastern United States. Today, most Americans have never tasted it. Many have never heard of it. And yet this fruit once sustained indigenous nations, colonial settlers, soldiers, and freedom seekers alike. It did not vanish because it was inferior. It vanished because the world changed around it. Music deepens. Long before European ships reached American shores, pawpaw was already home. Archaeological evidence from Russell Cave in Alabama shows pawpaw seeds dating back more than 8,000 years. Indigenous nations did not treat it as a lucky accident of nature. They understood it, they managed it. They spread it deliberately along trails and near villages. The Shawnee marked an entire month in their calendar for the pawpaw harvest. The Powhatan word for the fruit, asimin, would later become the root of its scientific name, a quiet reminder of whose knowledge came first. These communities recognized pawpaw not as a novelty, but as a dependable staple. It ripened reliably at the end of summer, precisely when other food sources grew scarce. Its calories were dense, its nutrients were abundant, and its trees, once established, required no tilling, no chemicals, no fences. This was not wilderness food in the modern sense. It was agriculture shaped to the rhythms of the forest. When Spanish expeditions pushed inland in the 16th century, they noticed. In 1541, as Hernando de Soto's expedition moved through the Mississippi Valley, chroniclers recorded native communities cultivating pawpaw in managed groves. These were intentional plantings, selected trees, living orchards integrated into the landscape. Pawpaw was already part of a food system that worked. Plants stand directly in this field. Their leaves, coated in wax and fine hairs, interact with charged particles in the air. Their roots connect to the negatively charged soil. Each plant becomes a bridge, a living conductor between two poles of a vast natural battery. This is not metaphor, it is measurable reality. Instruments can detect faint currents moving between air and ground through vegetation. For most of history, this background electricity was ignored, dismissed as irrelevant noise. But early 20th century experimenters began to wonder whether life had evolved not just to tolerate this field, but to use it. Inside plants, electrical signals already play a crucial role. When a leaf is damaged, a wave of electrical activity travels through the plant, triggering defensive responses elsewhere. Growth itself is regulated by electrical gradients across cell membranes. Even tiny changes in voltage can alter how cells divide, how nutrients are transported, how genes are expressed. If plants already respond to electrical cues, the question becomes unavoidable. What happens when those cues are amplified? A copper wire, after all, is far more conductive than a stem or a leaf. Placed into the soil, it can collect atmospheric charge more efficiently and deliver it directly to the root zone. Shape matters too. Spirals, found everywhere in nature, act as antennas. They gather energy across space and focus it inward. This is why early electroculture devices often looked more like sculptures than tools. Christoffel and others believed they were not forcing plants to grow, but unlocking pathways evolution had already built. Letting physics and biology cooperate instead of compete. For a brief window of time, this vision had momentum, until another force entered the field. In the aftermath of World War I, industrial chemistry surged forward. Factories that had once produced explosives were repurposed to manufacture synthetic fertilizers. The Haber-Bosch process made it possible to extract nitrogen from the air and turn it into ammonia at unprecedented scale. Yields soared, costs fell. Fertilizer became cheap, portable, and endlessly repeatable. But it also came with a new economic logic. Unlike a copper wire installed once, fertilizer had to be purchased every year. Sometimes multiple times a season, the model rewarded dependency. As chemical inputs flooded agriculture, alternative approaches quietly lost institutional support. University funding followed industry priorities. Journals grew skeptical of methods that could not be monetized at scale. Electroculture, once investigated by government committees, was reframed as fringe curiosity. Photographs of giant crops were no longer evidence. They were anecdotes. Inventors were labeled eccentrics. The conversation shifted from results to ridicule. By the late 1930s, electroculture had faded from mainstream science. Not disproven, simply ignored. For decades, it lingered in obscurity, passed down through obscure books, backyard experiments, and whispers among unconventional growers. And then, quietly, something remarkable happened. In the early 21st century, researchers in China began investigating the effects of atmospheric electricity on crops, not in gardens, but across thousands of hectares. Using suspended wires designed to enhance the natural electric field above farmland, they conducted large-scale trials under controlled conditions. The results were not subtle. Yields increased by nearly 30%. Pesticide use dropped dramatically, in some cases disappearing altogether. Plants showed improved resilience, fewer pests, stronger growth. All without additional fertilizer. This was not folklore. It was institutional research, published, measured, repeatable. The experiments did not rely on dangerous currents or artificial power. They worked with the same natural gradient that exists everywhere on Earth. The same force Christoffel had tried to harness a century earlier. At Hidden Nature Vault, stories like this reveal a pattern that repeats throughout history. Innovations that offer abundance without dependency often face the strongest resistance. Not because they fail scientifically, but because they fail economically. It is important to draw a clear distinction. There are electroculture systems that use high-voltage power sources, and these carry real risks. But passive systems using only atmospheric energy are fundamentally different. A simple copper spiral placed in soil does not generate electricity. It collects what is already there. Gardeners experimenting with these methods today describe modest but consistent changes. Healthier leaves, fewer pests. Improved growth, nothing explosive. Nothing dangerous, just subtle shifts that hint at deeper mechanisms still not fully understood. The cost of such an experiment is trivial, the implications are not. Modern agriculture consumes hundreds of millions of tons of synthetic fertilizer each year. Soil health declines. Waterways choke with runoff. Farmers face rising costs and shrinking margins. At the same time, the planet hums with free energy flowing endlessly between sky and soil. The question is no longer whether plants respond to electricity, they do. The question is whether we are willing to revisit ideas abandoned not by evidence but by economics. Christoffel's copper wires did not disappear because they were disproven. They disappeared because they did not fit the system that replaced them. Music softens. The fields remember what we forget. The sky still holds its charge, the soil still answers, and the space between them remains alive with possibility. If the future of food depends not only on what we add to the earth, but on what we learn to listen to, then rediscovering these forgotten pathways may matter more than we think. Sometimes progress does not require invention, it requires attention. And if this story sparks something in you, a curiosity, a sense of wonder, or a desire to see the natural world differently, stay with us. There are more forgotten truths waiting to be uncovered.